Hello and welcome to today's demo. Today we will be looking at a composite part. This is a twin turbo intake manifold, and as we can see this was modeled as more than just a manifold. We also have some set screws here. We've got ratchet straps, and we also have the air filters on here. This particular part was not modeled inside of Rhino, so this has been imported as an STL, or sorry, a step file, and resaved as a Rhino 3DM. So because it wasn't modeled inside Rhino, we're going to have some cleanup that needs to be done before we can actually proceed with flattening. So the first step is to remove the unneeded geometry. So because we're only flattening the manifold, this part here, we need to remove everything else. So we can either select everything else, or we can select the manifold. We can just invert the selection. In this case, we've selected the filters, we've selected the ratchet straps, and we've got the set screws here, and we can simply hide these or delete them. When we start looking at the manifold itself, we can also see that the manifold has thickness to it. So when we look at where the filter is attached, we can see the thickness. And when we look down here at the mounting plate, we can see we've got quite a thick plate down here. So we're also going to need to remove the thickness. We're also going to remove a good portion of the mounting plate for flattening purposes, just because we're not going to be doing this from the carbon fiber. So our next step is to basically explode our surface here. This came in as a block, so we have to explode this to remove the block reference and to separate the poly surface out into individual surfaces. And once we're done all that, we end up with a single surface very much like this. So I've already done the work of separating this out. So what we have here is a single surface. We've removed the filters, the ratchet straps, and the set screws here. We've also removed a good portion of the mounting plate here. So with ExactFlat, the standard workflow is to first get your surfaces that you want to flatten. You need to create splits in the surface where you want your seams to be, and then we join it all together into a single poly surface. When we mesh a poly surface, we get a much better result. We have continuous mesh vertices and shared edges across surface boundaries, which is ideal for ExactFlat. So we join everything together as a single surface, and then we use the Rhino mesh command to create a mesh. So we can use simple controls, and we can simply drag the slider over to more polygons, and when we click preview, we get a decent mesh. But when we start looking at the mesh, we can see we have a lot of high aspect ratio triangles, and when we look at the quads, we have very, very strong rectangular quads that are very far away from being square. So even though ExactFlat will work with this, what can happen is when we start to use the Adaptive Remesher to recondition this mesh, because we have very, very large triangles here, right up to right next to very small elements, we end up with an uneven sampling across the surface of the mesh, so we can get unpredictable results. In most cases, the Adaptive Remesher won't have a problem and will create a good mesh from this, but on occasion, we can get meshes that just do not adaptively remesh nicely, or just have errors in them. So the easiest way to prevent this is to instead use detailed controls. And the most important thing is to change the maximum aspect ratio to about 2. So what the maximum aspect ratio does is it just controls the aspect ratio of the triangle. So when you start considering the shortest edge of the triangle against the longest edge, the aspect ratio is how much longer the longest edge is. So when we set this to 2, we're basically saying that the longest edge can be at most twice the length of the shortest edge. And this is going to help control our triangle shape and size, as well as quads. So the other thing we're going to change is the maximum and minimum edge length here, and these are best to be set with the size of the mesh. So if we rotate our view so our construction plane is perfectly normal to our camera here, we can just kind of use the coordinates down here and move our mouse around to get a sense of scale. So when our mouse is over here, we're around -50 on the x-axis, and when we're over here, we're around 50 on the x-axis. So this part is about 100 millimeters wide, and if we move our mouse up here, we're at about 120 on the y-axis, and down here we're at about 10 on the y-axis. So we're about 110 tall. on this part here. So given that, we want to make sure we have a fairly good sample spacing along here. So based off these measurements, if we start, it's best always start high. So we'll start for maximum edge length of around 10, and we'll set our minimum edge length to 1. And if we hit preview now, we're going to get a new mesh, and we can see that we've got a much more uniform distribution. However, our elements are still fairly large, so I prefer to have a bit smaller element spacing. So what we're going to do is we're going to cut this in half. So we'll do 5 for maximum edge length, and we'll do 0.5 for minimum edge length. And now when we hit preview, we've got smaller elements, but they're still a little too large. We didn't really decrease the size that much, so we're going to reduce this even further. So we'll do 1 and 0.1, and now when we hit preview, we can see we have a much finer element distribution here. So our quads are now all more or less square, and they tend to match the size of the triangles here. So this is a really good mesh to start with for the Adaptive Remesher. So we're going to go ahead and we're going to accept this. So because this part was created from an import file, it was imported as a stepped file from a CAD package outside of Rhino. We do have a few meshing errors. So instead of showing the process of repairing these in the video, because it can take quite a while to identify and fix them all, I've already gone ahead and created a mesh and repaired all the errors, so we're going to be working with this mesh. I have also filled in the holes here where the set screws were, and I've also preserved their boundaries as curves here. So with ExactFlat, even though we can flatten pieces with holes in them, it's usually better to fill those holes in and preserve the boundaries of the curve, and we can trace those holes back onto the flat pattern afterwards. By filling in the holes, we're going to be simplifying the geometry that's going to be flattened, so we're going to make it easier for ExactFlat flatten this. We're going to decrease the amount of time required to optimize, and we're also going to allow the optimizer to give us a bit better of a pattern that's going to sew together at all the seams here. So from here, we're going to go ahead, we're going to select our meshes. And instead of remeshing these outright, if we do have an issue with the Adaptive Remesher, it's always good to have a copy of these. That way we can go back to them and make any kind of repairs and remesh again. So we're going to select our meshes, and we're going to use the copy to layer command, and we're just going to copy these to the remesh layer. We're going to create a copy of them, and we're going to remesh a copy. So now we're just going to, again, we're going to rectangle select everything, and we're going to switch over to the Mesh Tools toolbar, the ExactFlat toolbar, and we're going to use the Adaptive Remesher. So the first thing we're going to do before we start changing settings here, we're just going to go ahead, we're going to click the Start button. This is going to create a remeshed version of the mesh, and it's going to tell us how many vertices we have. It also gives us a way to visualize the part, and it gives us a basis for determining whether we need to reduce the tolerances or increase the tolerances. So if we have too many triangles here still, we're going to want to increase the tolerances. We're going to increase the maximum allowed distance between the original and new surface and boundary. Or if we need additional triangles to preserve features that have been removed, then we're going to want to lower our tolerances to reduce the allowed distance between the new and the old mesh. So in this case, we're down to about 480 vertices on our largest mesh. So we do have some room to improve the fidelity and to add more triangles while still creating a mesh that's going to flatten very well with ExactFlat. So we're going to go ahead, we're going to reduce these here. We're going to cut them roughly in half. So I'm going to say 0.7 for these here, 0.7 and 0.7, and it's best to always keep your minimum edge length the same as the smallest value between the surface and boundary tolerance. So we'll just go ahead, we'll click Start again. We're going to restart the remesher, and we're going to create new meshes here. So it's analyzing the mesh again, and now it's giving us our estimates and creating the mesh. So we can see that we've got more triangles here. It's preserving the curvature a lot better, especially down here where the two intakes meet up. So this is a good result. So we're going to go ahead, we're going to click OK. And if we rotate around, we can examine the quality of the mesh here. So one thing we'll notice is that we've got a lot of areas where we tend to have zoning of the triangles. They tend to get very small. So these these can be fixed, or you can leave them as is. We haven't created a huge number of triangles here, but if we undo the remesher, we can see that these areas all correspond to locations where the Rhino mesher has created a very large number of triangles. So this is the predominant source of errors, and this is what I spent most of my time fixing on this mesh before flattening it. So that the easiest way to fix these errors, so this particular area here, if we redo our results, we can see that we've got one spot here in particular that's being highlighted. So we've got some kind of meshing anomaly here, and we can see that corresponds directly with this spot right here. So probably we have a very, very thin, small triangle right here that could be removed. So what we'll do is I'll do a quick repair on this mesh right here. So the easiest way to deal with these kinds of problems is to simply remove the triangles. So in the case of this mesh here, what I'll do is I'm just going to align it so I'm going to remove or simplify this entire strip right here. So I'm going to try to make this perfectly horizontal as best as possible. Now what I'm going to do is I'm going to use the points on command. Points on. And this is going to allow us to start selecting vertices and manipulating vertices. But instead of manipulating them, what I'm going to do is I'm just going to select all these vertices right here, because we know we've got some kind of problem in there. And if we actually rotate around, this is a fairly planar surface here. We don't have a lot of curvature. So the easiest way to deal with this is to simply delete the bad vertices. And now what I'm going to do is I'm going to use the Rhino fill mesh hole command, and I'm going to fill this in. So it's going to greatly simplify. We've probably removed a couple hundred vertices there and replaced them with maybe 20 triangles. So this is a very great way to fix these kinds of errors. So now what I'm going to do is, because we've filled the hole, we actually created a disjoint mesh here. So it's created a separate mesh here and joined it together. So we've got duplicate vertices all the way along the edges here. So we're just going to use the Rhino weld command to fix this. And now if we go to remesh these, I'll use the cell mesh command to select everything. We'll adaptively remesh. And we'll go back to our original settings. So we'll go 0.7, 0.7, 0.7. And now if we create our mesh here, we'll notice that our estimated vertex count is going to be reduced for this piece, and we'll actually see that we no longer have that localized zoning there. So that's the easiest way to fix the mesh errors. We could do the same thing over here, and if we again undo, we're going to see that that particular spot corresponds to these triangles here. So the easiest way to fix these errors, and in this case these aren't too bad. Some of the errors that I did fix, we had very small or fine zoning, so we had to remove them. But in the case these aren't too bad, if we undo here again, we can see that that area once again corresponds to an area of lots of triangles here. So again, the result we got from the adaptive remesher redo, it isn't terrible. We do have a bit of zoning here, but we don't have excessive zoning, and we still have a very reasonable number of vertices and triangles on this mesh. So it's not worth spending the time to remove all these errors fully. But if you did need to remove them, the easiest way is to simply delete the vertices associated with all those triangles and just fill the hole in. So once we've adaptively remeshed, the next step is to flatten using ExactFlat. So we're going to switch over to the Tools tab of the ExactFlat toolbar, and we're going to use the very first icon here. This is the Flatten command. So ExactFlat is a two-stage flattener, and by that, the first stage is a very quick pre-flattening. So ExactFlat has two different sets of flattening tools. The first step of pre-flatteners are what we call preflatteners, and we're seeing the results of a pre-flattener right now. So the pre-flatteners very quickly create an unoptimized flat pattern that may have folds or wrinkles or flipped triangles in it. And the whole purpose of the pre-flatteners is to be very fast. So we can use the pre-flatteners to produce new flat patterns. And what we're seeing right now is the results of our fracture pre-flattener, or sorry, our press pre-flattener. And ExactFlat does have multiple pre-flatteners. So in the toolbar, we've got our fracture pre-flattener right here. We've got our pelt pre-flattener, and we've got our suite of CCM pre-flatteners. We also do have a couple pre-flatteners that aren't in the toolbar yet. However, the three in the toolbar are by far the most useful and work pretty much all the time to give you the best flat pattern. So once we're done with our pre-flatteners, we'll move on to our optimizer, and this is the second flattener that we have, and it's a much slower flattener, but it's the one that's always going to give you the final optimized shape and reduce your average energy density to as close to zero as possible. One of the conditions of using the optimizers, though, is that we cannot have any flipped triangles. So when we look at our pattern pieces here, we can see we have a lot of black crosses, and these indicate flipped triangles or folds or wrinkles in the pattern. So these need to be removed before we can use the second stage flattener, the optimizer. Also, the performance of the optimizer depends entirely upon how much strain it has to remove. So when we look at the color of these pieces here, the color represents the relative amount of strain on the pattern piece. So the default legend for ExactFlat has white indicating 0 strain, cyan indicates about 5% strain, green indicates 10%, yellow indicates 15%, and red indicates 20% or more. So we have quite a bit of strain on these pattern pieces. And the best way to think of strain is if we think of our original 3D model as a rigid form, a plastic shell. If we were to stretch these pattern pieces back onto the shell, the more strain we have on our pattern, the more we're going to have to pull them and stretch them to get them to fit back on. So really, when we have a lot of strain, it just means our pattern is too small, it's not going to fit onto the piece. So when we think of this in terms of our pre-flatteners, the two biggest goals for our pre-flatteners is first and foremost to remove flip triangles, so all these black crosses here, and the second biggest goal for the pre-flatteners is to reduce the strain on the pattern pieces. So if I were to use our pelt tool here, if I were to pelt this piece here, first of all, we're going to notice that we no longer have the crosses or the flip triangles. Second of all, we've reduced some of the strain, although we still do have quite a bit of strain on this piece here. So we could try a different pre-flattener here. So we'll try our CCM initial and see if we get a better pattern here. And in this case, we've got, we actually start to see a bit of black here. And black indicates sag. So this is the complete opposite of strain. This means we have excess or more material than we need. So in this case, none of our pre-flatteners, fracture is not going to give us much of a better result. We do have a lot less strain with fracture, however, we do have flip triangles. So one thing we can try is we can try to remove the flip triangles with our CCM tool, minimal pre-flattener, or we can use our automated flip triangle removal. But for this part, pelt tends to give the best results. So we'll try fracture on a few more pieces. And the other thing with fracture too, we can use our pre-flatteners as many times as you want, on as many pieces as you want, so long as you optimize your pattern pieces after you pre-flatten them. So the typical ExactFlat workflow is once you've flattened, you can use any of the tools at any point in time that you want, whether it's a pre-flattener or some of our cutting tools or vertex manipulator, so long as optimize, our second stage flattener, is always the very last thing you do. Because the optimizer is going to optimize your pattern piece for best fit, it should always be last. So we're going to go ahead, we're just going to pelt these pieces here because we know pelt gives a good pattern, and we'll do the same to this one over here and this one here. So for all these pieces, we've removed all of the flip triangles, or folds and wrinkles. We don't see those hatches anymore, and we've produced a pattern piece that doesn't have huge amounts of strain, although we could produce patterns that have less strain. In this case, because we've got a lower vertex count, we're all under 1,000 vertices, even if we do have elevated strain values, ExactFlat's still going to be able to handle this just fine. So sometimes it could be difficult to spot flip triangles, especially if we have a lot of sag on the pattern pieces. So one easy way to do this is to switch over to the Highlights tab of the ExactFlat toolbar, and we're going to turn off our strain analysis. Oftentimes too, you'll have the edge highlight turned on, so this is what it looks like with the edge highlight turned on. You can actually see the edges. So if this is the case, you can turn the edge highlight off as well, and this makes it very easy to spot folds or wrinkles or flip triangles on the pattern piece. In this case, we don't have any folds or wrinkles, so we don't have to do any additional work. So we'll turn the strain highlight back on, and we're going to go back to our Tools tab. At this point, because we're dealing mostly with our pattern, what I'm going to do is I'm going to minimize our perspective viewport. So I'm going to do this by double clicking on the viewport title. And now we're going to go over to our top viewport, so we're looking straight down at our pattern piece. And I'm going to maximize this by double clicking on the top viewport title. I'm also going to go over to our layers tab, and I'm going to make the pattern layer our default layer, and I'm going to hide the remesher model, and I'm going to hide the 3D reference model as well. So now we're only looking at our pattern pieces here. So we've accomplished our two goals using our preflatteners. We've reduced the strain a little bit, and most importantly, we've removed all the flip triangles. So now we're going to go ahead and we're going to use the optimizer to minimize the average energy density. So we'll start the tool, we're going to select all our meshes, and we'll press enter to accept the selection. And we're going to go ahead, and for this part, I don't have any carbon fiber material or fiberglass or any kind of composites in our default database, so we're just going to use a simple cotton. But when you use ExactFlat, if you've had your material analyzed or if you want to choose a different material, we can click the Browse button to open up a material browser, and we can choose from one of ExactFlat's default 85 materials or one of your materials that you've created in the ExactFlat library yourself. And when you're done, just click OK. And we can start the optimizer by clicking OK here. And this is going to open up the spring status. So as this is running, we're going to notice that both the colors are changing and the shape of the pattern piece is changing. So what's happening here is ExactFlat is expanding the piece, so it's either adding material or removing material, and it's basically changing the shape of the piece to optimize the fit onto the original piece. So again, if we think of our 3D model as a rigid plastic shell, is changing the shape so that when we lay this pattern piece back on the rigid shell, it's going to fit with such that we don't have we have to pull or stretch it as little as possible. So we can see the colors are changing, and this is because the shape is changing, which means the amount of strain on the pattern piece is also changing. And we can see this in the optimization report. So piece 1 is finished optimizing already. We're on to piece 2. So I'm going to go back to piece 1 here, and we can see different information being reported for our pattern piece here. So probably the most important piece of information is our average energy density. And right now it's telling us the average energy density for our first piece is about 0.8 Newton meters. So this is a very low amount of energy across the entire pattern piece. We also have a maximum energy density, so it's the single point of maximum energy or most strain on the pattern piece, and that's at about 50 Newton meters. So this one, although it's an important piece of information, it's not as important because we can artificially increase the maximum energy density just by manipulating an interior vertex. Really, it's the perimeter that we're worried about when we optimize our piece. So the maximum energy density at 50 isn't a huge problem. If, for instance, we had a maximum energy density that was, say, 20,000, that's going to be a good indicator that we've got some kind of meshing error, and that's going to be a problem that's going to have to be fixed. That may be the result of overlapping triangles or an impossible surface to produce. For instance, we might have some kind of loop built into our mesh. That's when we're going to start to see very, very high energy and maximum energy densities like that. The other a couple pieces of information that are important would be our no seam stretch error. So the dialog does report the boundary length of the 3D model piece, and the no seam stretch error is basically the difference between 2D pattern perimeter length and 3D model perimeter length. So right now, after we've optimized this pattern piece, our pattern perimeter has changed by about 8 millimeters, which over the size of the piece is not a huge error, and depending on the material being used, especially like a cotton, the materials are stretchy, so that error can definitely be taken up just by the stretch or expansion of the material. If you're working with materials that don't have any kind of stretch, so like a composite weave, typically doesn't stretch at all in the warp or weft direction, but it can deform on the bias direction. So when working with those materials, it's best to have your no seam stretch error as close to 0 as possible. And if you're not getting decent results just with the default settings, when we go back to the pre-spring settings, I'll just start the optimizer again here on one piece. we can turn on a preserve boundaries option, and this allows you to constrain the no seam stretch error to within an acceptable tolerance. So we can say that we want at most 5 millimeters of error between our model and pattern perimeter length, and the optimizer is going to constrain the perimeter length to at most 5 millimeters. So optimization has completed for all of our pieces, and we can see that the color and shape of them have all changed. So we've greatly reduced the average energy density for these pattern pieces simply by optimizing them. So at this point, we can rearrange our pattern pieces to help us with the patterning. So one easy way to do this is we can just simply rotate the pattern pieces using Rhino. So in this case, I'll use the rotate command. And I'm just going to choose one of the vertices here, and I'm just going to use this as a selection point to rotate the pattern piece. I can also use the ExactFlat find tool, and this helps me find neighboring pattern pieces. So with this tool, I'm just going to rotate this again right here. So I'll select these 2 points and I'll make this perfectly horizontal. So I can snap my selection points to either be perfectly horizontal or vertical by holding the shift key on the keyboard. So now I'm going to use the ExactFlat find tool. I'm going to find the neighboring pattern piece. So you'll notice that as I mouse over here, it's going to automatically find the neighboring piece for me. There we go. So I'll just rotate these here. So this is how these pieces would come together, just like this. So at this point, and depending on your patterning workflow, you may be using Optitex software or Gerber or AccuMark for doing your patterning work, in which case you can simply create a DXF and start your patterning process in another package. However, ExactFlat does provide basic patterning tools. So first of all, before I forget, we did remove the holes. We did have holes for the set screws. So if we go back to our model layer here, we no longer have holes in our 3D model. I'll go back to our perspective view, but we did save the location of these holes, and they're on the holes layer. So we can see we've got these 2 holes here, and they are curves. They do lie on the surface of the mesh here. So what we're going to do is we're going to trace these holes onto the pattern pieces, and to do this, we're going to use the ExactFlat trace command. So we're going to start the command by clicking on the icon, and we're just going to start by selecting the first curve. It's important to note that the command line is always going to tell you what is expected, so it's best to read the command line when you're using ExactFlat commands. It's going to tell you what needs to be selected to perform the action. So we've selected our object that we're going to trace. In this case, it's a curve. We're going to trace it onto this model piece, and at this point, we're given the option of defining our curve fit tolerance. When I created this curve, I simply duplicated the mesh border, so we created a polyline. So the curve fit tolerance has no role here. However, if we were tracing a spline or curve onto the mesh, then the curve fit tolerance is the way of defining how many points we want when we tessellate that curve into a polyline. So we're just going to go ahead, we're going to click OK, and very quickly we've traced this curve onto the 2D pattern. So if we make our pattern visible, we can see this is the perfect location traced from 3D to 2D of that hole. So we'll repeat the process again. We'll use this curve over here. So we're going to trace that curve onto this pattern piece, and we're just going to accept the curve fit tolerance, and very quickly we trace that hole onto the pattern piece. So we can use the ExactFlat patterning tools to add things like notches, and in this case we've used our patterning tools to trace the location of our holes back onto the pattern. So this tool can be used to indicate the location of different hardware items, in this case the set screws, and the location of the hole that needs to be cut out. We can use it to indicate the location of labels or mark where things need to be sewn. We can use it for annotation purposes if you need to indicate a seam line of some sort, or the start or stop of a zipper, for instance. You can use the tool to indicate or create a marking on the pattern to indicate those locations. We can also use our notching tools to add notch or alignment markings to the pattern piece. So we just start the tool by clicking this icon here, and the default settings can be changed. So this is the default template used for all of our notches that we're going to be adding. So for this one here, we're going to set the notch text that's going to be created as simply a unique auto-incrementing number, and we're going to create red slit notches. So we're going to go ahead, we're going to click add, and as we start adding our notches here, we're going to notice the notches appearing on both the left and right hand side of the cut. This is because ExactFlat builds associations as it's flattening, so it knows which two pieces sew together. So as we add notches to one side, ExactFlat is going to automatically add that notch to the other side. So when we're done adding all our notches, we just press enter on the keyboard, and we can see all the notches that we've created in the list here. So once you're done adding your notches and adding all your markup to the pattern, we can create a DXF by using the ExactFlat DXF export tool. This tool is different from simply saving your part as a DXF. When you export a part with ExactFlat using the DXF export tool, all the hardware markings that you've traced on, all the notches that you've created, any kind of tags that have been created, all this information is transferred to the DXF, whereas if you just simply save your file as a DXF, you simply get the perimeter of the mesh. You don't really get all that information that you've added. So it's important to use the ExactFlat DXF export tool, otherwise you're not going to get all your information in the file. We also get a seam allowance applied to our pattern piece when we export with the ExactFlat DXF exporter, and again that's information that's simply not created when you save your part as a DXF. So I've already saved one DXF here. I'm just going to select that file. I'm going to save over top of it, and now what we're going to do is we're going to import this file, and we'll compare the DXF that we just created with the pattern piece here. So I'm just going to use the Rhino import command, and I'm going to select our carbon twin air intake, and I'm going to import this into the document. So here's our part that we created up here. We've imported it into the document, and now we can see the work that we've done. So right away we can see that we've got a couple patterning errors over here. So if we line this up here, we can zoom in, and in this case this patterning error is probably created from right there. So we can see we probably, when I was splitting up my mesh, I missed a tiny little selection here. So because the way this offset was created, it's created some undesirable result in the pattern piece here. So we can either fix this in the pattern by eliminating that little piece, or what we can do is we can select our pattern piece here, and we can block edit this piece, and we can simply manipulate and modify the vertices to remove this patterning error. So in this case, I'm just going to delete the excess vertices here. I'll drag this over here. So it's very easy to fix these kinds of errors. And we'd have to do the same thing over here. So again, this kind of seam error was probably created because of the way this piece wraps around. If we zoom in, we probably are going to notice other small problems here that were just missed during the flattening process. But the information we're looking at here is for each piece, we're going to have a blue line and a red line. So the blue line represents our seam, which is the natural boundary of the pattern piece. So our blue line is going to line up perfectly with the perimeter of our pattern piece. We also have a red line, and that represents the seam line plus an optional seam allowance that has been added to the pattern piece. And we're also going to see that we've got a gray line here representing our grain line. So with ExactFlat, unless we manually add a grain line using our grain line tool, our grain line is always going to be the horizontal x-axis. So you can always align your pieces along the x-axis and assume that the x-axis is going to be the grain line. For our other pieces over here, we can see we've got our notches that we've created. So in this case, we've got our slit notches, and down here we can see they perfectly line up where the two pieces converge. So The reason the slits span the entire seam is because of our notching template. So when we look at our notching template again here, we can actually specify the notch length, and in the case of V notches, we can specify the width as well. But if you have a notch length of 0, it's just going to assume the length of the actual seam allowance that's been added. If you manually set the notch length, then that will control the length of the notch starting from the cut line. So you don't always have to cut your notch right from the cut line all the way to the seam line. You can manually specify the notch length as well. When we zoom in a little closer, we can see that we do have our notch tags here visible as well. So we have quite a bit of information on our DX here, on our DXF, and the most important thing is that all of this information is placed onto different layers. So when you import this into your nesting software, if you're using something like Eastman EasyCut, you can assign different tools to different layers. So you might assign a wheel blade to the cut layer. You might assign a pen tool or an airbrush to the seam layer. You may assign a drag blade to the notch layer for doing the notching. And your trace lines, in this case the trace lines are here because we traced the cutouts onto the pattern piece, so we may want to assign a wheel blade or a drag blade to the trace line layer. And notch tags, we can probably do a pen tool or an airbrush as well. Or optionally, you can just simply turn those off, or if you want to bring them into another CAD package, you can simply delete those layers if they're not needed. So all the information that's created is very segmented and placed onto different layers. So it's very easy to manage all this information in the DXF. And remove the information that's not needed, and deal with the needed information appropriately. So this has been a quick video on how to flatten this carbon intake. So to summarize, we started with a surface. In this case, it was a step surface that we imported from another CAD package. I had resaved as a 3DM before starting the video, but this was imported geometry from a step file. We hid all of the information that wasn't needed, so we hid the air filters, the tie and the ratchet straps, we hid the set screws, and we separated the top surface from the thickness and the inside surface. Once we had our surfaces, we created a mesh, and we repaired any kind of meshing errors that needed to be repaired. We exploded and recombined our mesh into logical pattern pieces, so our 4 pieces here, top, bottom, right, and left. And once we had our mesh, we used the Adaptive Remesher to create our remeshed version. So that's what the remeshed version looks like. We started off with this mesh here, and we used the Adaptive Remesher to create this. And this is the mesh that we used to flatten. So we also filled in the holes. That way we end up with a simpler pattern that optimizes quicker. So we flattened our adaptively remeshed mesh and used the pelt preflattener to remove all the flip triangles and a bit of the strain. And once we did that, we used the optimizer to get the final flat pattern shape. So thank you very much for watching.